Alright, this is homework 3, question 7, which is a multiple choice question asking to identify which of the 5 facts is false regarding these two complexes, given their respective colors violet and yellow. Now the first thing I would do in this situation would be to write out the nanometers of light of the wavelength given for violet and yellow. So we know violet is 400 nanometers, that's given from the color wheel on the test, and yellow is 590. Next, just looking straight across the wheel, you'll find that violet and yellow are directly across from one another. So the compound that appears violet absorbs yellow light, and the compound that appears yellow absorbs violet light. And that's good information to know. So I would start from the top and immediately see paramagnetism, unpaired electrons. That takes actual work. Chances are on a multiple choice question you don't want to waste the time. So I just skip all the way down to the bottom. It's asking if they absorb complement colors, which obviously they do because that's how light works. As light comes in, the colors that bounce off are what you see. The color that gets absorbed is the opposite what you see. So complement colors, absorbed, true, so that one cannot be correct because it's asking about what's false. Moving on, moving up, we're asked if this compound, the violet compound, transmits at 4,000 angstroms, which is a bit of a strange question considering we normally deal with light in nanometers and not angstroms, but that conversion can be done very easily. It's on the back of all the exams. And you'll see that 4,000 angstroms is actually violet light. Sorry, is that? Yeah, 4,000 angstroms is violet. And so if it appears violet, that means the violet light is what's getting shunted off over here, so it can't be the light getting absorbed or transmitted. So that one also has to be wrong. And then you move up to this where you get into a little bit more math, but it's still very easy, very doable. You know, delta O, or it's asking if the delta O of the violet compound is lower than the delta O of the yellow compound. And now here's where you have to look at which colors they absorb, because those colors are what determines how high that change in energy is. Now, as you recall, when you draw out the electron configurations, the delta O is this bit right here, sort of the difference between the low energy state and the high energy. And so when you want to determine how large this is, or at least how large it is relative to a different gap, is you want to see how much light has to get in there to bump this up a notch. So as you see from the wavelengths of the light, the violet compound is absorbing light at the yellow, so it's going to be absorbing at about 590 nanometers, whereas the yellow compound is going to be absorbing light in the violet around 400 nanometers. Now the nanometers show how spread apart the wavelengths are. So while you have the 590 spreading quite a bit and the 400 spreading a little bit, it seems a bit backwards, but the 400 is actually much higher energy than the 590 because it's much more condensed. So actually you have this yellow compound absorbing in the 400 nanometer range is absorbing much higher energy light and therefore taking much more energy into this here jump. So it's taking more energy to get across this jump, and therefore its delta O must be larger. So we know the yellow compound has high delta O, and the violet compound has a low delta O. Let's note that correctly. So back to the question. It's asking, does the violet compound have lower delta O than the yellow compound? And that's what we just determined. So great. We know that one has to be true because we're asking for what is false. And then we get up to this last one here that's asking if the delta O of the violet compound is calculated directly from the color yellow. But it's not. We just did that. We had to look for the violet nanometers and had to calculate it from that. So we know that it's not calculated directly from the from the wavelengths of the yellow light, because we first have to go jump across that color wheel to find exactly what it's absorbing. So we know that B is also true. We know that B is false because it is not calculated directly from delta O, and therefore B has to be the correct answer. Now, if you wanted to, you could go through the trouble of doing all the electron configuration and finding out how many unpaired they are and if they're paramagnetic or diamagnetic, but it's really not worth the effort because you can get through it much more easily by doing this sort of process of elimination and then finding the one correct answer. And there you go. That's about it. Just knowing sort of the basics of how light and vision and all that sort of stuff works. This is actually a fairly doable problem, and that's about that.